Example number 5, it says find the I can't say that word, parametrization of, for the line segment with the endpoints -2, 1, and 3, 5. Okay? And so if I were to graph this, these are the endpoints, right? So I'm going to go -2, 1. That's a point there. And then I'm going to go 1, 2, 3, and then I'm going to go up 5. Oh, I never really draw it to scale, do I? Well, that's not cool. So we're going to say 1, 2, 3, 4, 5. That's all right. We can sketch it. So what we need to do then is well, darn it, I'm going to have to draw the whole thing. It makes it better that way. Let's draw it to scale and we'll take a look at it. So I'm going to say -1, 2, and I'm going to go 1, 2, 3, 4, 5, and then 1, 2, 3. So I've got -2, 1 here. Okay, and then I've got 3, 5, which is about right here. And that is 3, 5. And I'm going to draw a line between the two. So I'm going to go from -2 to +3. Wait, whoops. And so I don't know. The y-intercept is somewhere in there. Okay. So I mean, if you do it on your graphing calculator with graph paper, it looks perfect. But that's okay. We know it's between 2 and 3, right? Yeah. We know we got to verify it algebraically, anyways. Okay. So the first thing that I want to do, there's a formula that we could use that'll help us solve this thing, okay? So it says using 2.1 we can create parametric equations. So if I say, yep, if I say x equals -2 plus a times t and y equals 1 plus b times t. Okay, this is my point x sub 1, y sub 1.
Is that like an equation?
Yeah, it's where it comes from is it's like an algorithm that'll help you find it. Basically, we have a function that looks like a linear function, right? And so linear functions have it's mx plus b, right? But if this is really like the point slope form parametrized, so that's where we start off if it looks like a line. Just keep that in mind. We'll do some more examples. So now what I want to do is if I solve this for t. If I solve for t, I'm going to add 2 to both sides over here. All right, and I'm going to get x plus 2 equals a times t, and then if I divide by a, I get x plus 2 over a. All right,
Can you move that up?
that equals t. Yep. And then if I do the same thing over here, I'm going to subtract 1 from both sides. I get y minus 1 equals b times t, divide everything by b, and then I get y minus 1 over b equals t. So what I've done is I've taken like a linear equation, there's some sort of slope, right? Now the reason for that is that we have a change. I could probably dive a little deeper and say that a linear equation has a constant rate of change, right? The slope does not change. In other words, the change in y never changes with regards to the change in x. It's always the rise over run. That's why we have this a times t. That is going to be like our x slope, or the change in x. There's a number that we're always going to multiply the x by and add it to this. Okay? And it's the same for the y. Our rise will always be the same. If you start at a point y and you go over go up so many times, that gets you to the next point y. Does that make sense to you guys? Mm-hmm. Okay. So now if I take both of those equations and solve for t, I get a relationship between x, y, a, and b, and t. In other words, I could set these two equal to each other. So if I come in here and I say, all right, then that must mean that x plus 2 over a is equal to y minus 1 over b. Oh, wait, not 2. X plus 2 over a is equal to y minus 1 over b. So now with that information, what can I do? Well, now I've got to figure out a way to come back and solve for a and b. Okay? So what we have here is we have a and b, which are two unknowns. Now I have 2 points on the line, so technically even though x and y are unknowns from the equation perspective, they're variables, I have values I could plug in. I could plug in an x and a y value from one of those 2 points or both. So I have 2 variables that are unknown. So how many equations do you need when you have 2 variables that are unknown? 2 equations. This is 1. All right? So we can think of this as like being equation number 1. All right, so since we need 2 equations, then our goal is to find a second equation and start solving for a and for b. Well, let's, there's a couple of ways you could do this. You could, if you wanted to, go back and solve for example, it says, then the line goes through the point -2, 1 when t equals 0, right? Because that's the lower boundary. So let's think this out loud. -2, 1 is the lower boundary based on our graph. So that occurs when t equals 0. We also know that the endpoint 3, 5, t must equal 1, right? Because the parameters, remember what they told us at the very beginning? That this was our beginning point, right? So this is like our beginning point. So that occurs when t equals 0, and then over here this occurs when t equals 1. I don't know if they define that, but that's an assumption that we can make. Yeah, because it's just a line segment. Okay? Sometimes they'll define it differently. And so now if that's the case, what could I do? How could I solve that? Okay? Well, my endpoint would have to be, in other words, for example, I could say 3 equals -2 plus 1 times a, right? And that comes from our previous equation, x equals -2 plus a times t. So if I evaluate this, in other words, this is my x equation, I already know what my y value will be. What will my y value be when x equals 3? 5, right? So y equals 5. But guess what? If I subtract 2 from both sides, what does a equal? A equals 5. Okay? Now if I take the second equation, which is y equals 1 plus b times t, and I plug in the y value, which is 5, what does my b value equal? B equals 4. So then if I have x plus 2 all over 5 is equal to y minus 1 all over 4. I've now eliminated my t's. This is how I could solve for the Cartesian equation. Or I could leave it as a parametric equation, because the original parametric equations that we started off with was x is equal to -2 plus a times t, and y is equal to 1 plus b times t. But we said that a is equal to 5 and b is equal to 4. So this is our parametric equations.